make sure you're on the right track, but that's about it. Okay, so we know that sticky molecules. We know that we have chemical means of reactions, but we also have chemical means of separation of chemical compounds, right? If we're dealing with separation techniques, we're generally dealing with mixtures. Mixtures are not chemically combined. Mixtures are physically combined. Physically combined means you can separate them in various methods. The one we are doing today is obviously which one? Chromatography. Okay. So filtering is going to be a physical separation method between, am I videoing? Yes, I am. Okay. Solids and liquids, and that's what we do daily when we dispose of waste, right? My honors kids are like, how do I get this out of here? It's like, filter it, people. We've been filtering for like a month now. Okay. Distillation. Distillation works by different boiling points or vapor pressure points. So basically, you heat something, the lowest vapor pressure, aka the lowest boiling point, will come off first, and the rest of the liquid will stay in solution. You heat it up more, the next solution or the next solvent at that particular temperature will then boil off. So you can separate things from boiling as well at a slow rate. And I might have you guys help me one of these days. I need to set up a distillation for an honors chem Mythbusters project. We're distilling ethanol. We're making ethanol from yeast and sugar. So they want to do it, and I was like, all right, so I got to set up a distillation, and you guys should probably know what the heck you're doing when you get to organic chemistry, because you're all going to make 6s on the AP exam. Yeah? 6s? Blow it out of the water, people. Blow it out of the water. Okay. So, chromatography, you can't make a 6 now. No, but we're going to blow it out of the water, okay? That is the goal. Or the lion gets you. Every time the lion was creepy.
It is creepy.
It's now looking at you, Krista. Okay.
No, but it's still weird.
Paper column. Okay, I have a little baby set up, and I'll show you in just a second. You have a paper that has some sort of interactive component to it. Like most paper is made of cellulose, so it's got some C, H's, and O's on it. So probably like a hydroxyl group or a ketone, something like that. Okay, so that's on you guys to help yourself figure out. And I also have like TLC. TLC is thin layer chromatography. It's like a chromatography paper with a layer of silicon dioxide on the top. It's got like nanoparticles on it. We're not going to use that today, but that's something you'll use when you get to big boy chemistry, okay? Or big girl chemistry, whatever. All right, so this is your lab. Basically, you know that there's a CSI team that is investigating some substances, and you're team B, but really you're the A team, okay? You're following up on them and what their results were. So you're going to be repeating the results and basically figure out the best solvent to separate the particular physical mixture we have created, which is just red 40 dye, yellow 5 dye, and blue 1. I think those are the right numbers. It's just a bunch of food coloring, but it's actually Kool-Aid, and I have it in the back for it's just a mixture, okay? But the couple of things you need to be aware of and make sure you're doing your greenness, thinking about the greenness as you go, think about the best solvent based on greenness and ability to separate. So you got to be thinking about all these things throughout your lab. You're only getting 2 solvents. If you want more than 2 solvents, please go for it if it's going to help you answer your questions. So you'll have some time to think about those at the end. And if you want to run another sample, I've got enough of everything for you. But you're only getting 20 mils of each sample. Okay? So you're going to get 20 mils of ethanol, but that's more than enough. You should probably, if you want to run 2 trials of that, put 10 and 10 in 2 different test tubes. What did I clicked that. Okay, so this is everybody. You guys already know what you're testing. If you want to test something other than that, that's fine, but you have to do that so we can have some comparative data. And this is just from the college where they like for us to occasionally show you why are we doing these inquiry labs. So these are like objectives these are objectives that we have to accomplish. And so there's a lot of crossovers. This one's very much focused on the IMFs, focused on ability of solvents to attract solutes and the IMFs between them and pull them apart. And then talking about the green chemistry aspect. So there's a lot of stuff we're talking about today that's overall a broad concept we have to be able to apply. Very qualitative though. All right, you know how chromatography works because you watched the video? The solvent front you have to keep an eye on. You'll use a pencil, and I looked through a couple lab procedures. I just didn't get a chance to look through all of them today. But it's pretty easy. That's why I didn't look at them last night. Mainly because I was out until like 8 p.m. doing stuff. Anyway, so you guys need to mark your solvent start point, solvent front. You need to get the RF values based on the distance traveled of the solutes, which are the dye particles. You read all that in your enduring understanding. If you didn't, then go back and look at it for how to calculate RF values. So, from a review standpoint, this is like one of the first pre-lab questions that I didn't ask you guys to do because I was going to talk to you guys about them. What is water creep over paper? Go. Capillary action. What's attracting what? It is adhesive and cohesive. Very good. So water is adhesive water is cohesive with itself, but adhesive to the paper or glass, for example. But what's attracting? Like, what's the IMF present? Water. Hydrogen bonding. Okay, so it's hydrogen bonding with the cellulose on the paper. It's kind of hydrogen binding to like a glass surface, which has free oxygen groups of silicon dioxide, or with itself, of course, is hydrogen bound. Yeah.
Wait, do you make water for going up
I'll show you a capillary tube in a little bit. That's how plants get their water to the top of the trees.
Plants aren't glass.
Sorry, it's just but it's capillary action. Yeah, water. But you know how water makes a meniscus? That's basically what I'm talking about. I'm not saying it's gonna like climb up and out and like go by, but I'm talking about it climbs the walls and makes a meniscus.
You just put the glass piece and you start going up like it's water.
I do have the smaller the capillary tube, the more it climbs. Yeah, like I have capillary tubes that are really teeny, and that's what happens. So yeah, they do attract, aka meniscus. And this was like the part of the pre-lab. You saw the molecules given here. So with this, how would water interact with this part of the molecule? This ketone right here. Actually, that's more of a carboxylic acid. But how would water interact with this oxygen? Through what process? It's actually going to be more the dipole-dipole, because you know hydrogen bonding is dipole-dipole on steroids. Yeah. Hydrogen bonding is just an extreme case of dipole-dipole. So it would interact with the oxygen, which has lone pairs, with the H attracted to it. Okay, this attraction, this H is attracted to this lone pair. That right there is actually dipole-dipole interactions. Because don't forget, water and other things, they experience everything. Okay, they experience London dispersion, dipole-dipole, and hydrogen bonding. So you can still say dipole-dipole, despite the fact the most prominent of all IMFs on this one, on water in this case, is hydrogen bonding. Okay, so then up here, this one definitely will experience what interaction with water? This group right here. Be sure of yourself. Yeah, that's hydrogen bonding, because it's an OH group like this. So that's qualifying as hydrogen bonding with this one, because the interaction occurs between the H and this O. Okay? There's literally nothing between there. You know this. I had to tell my honors kids again and again. They keep wanting to put a hydrogen between two things. They call it a hydrogen bond. Like, no. It's like literally nothing. It's just an attraction. It's like, I look at you, you look at me, we attract. And then over here, we've got a free C and O bond. That right there will interact with water via what? Dipole-dipole, good, because there's no hydrogen here even to interact. Yeah.
So only if there's a hydrogen next to it, though, it will be hydrogen bonding?
Mm-hmm. Or if it was like HF, NF, or OF. I mean OH, you know what I'm saying. All right, so this one's got ability to hydrogen bond on this side. What on this side? Dipole-dipole, dipole-dipole. So there's different components or different IMFs around a humongous molecule, especially when you get something big and bad like this guy. Citrate? What's this? Cornstarch polymer. Okay. So across the spread, you see different functional groups. So this hydroxyl will interact with water via hydrogen bonding. But this, I feel like this is a carbon. This is an ether group. Sorry, ether group. Ether group will interact with water via what? Dipole-dipole. But I'm saying water is my most common solvent. You're going to have to do this, but for ethanol, isopropyl alcohol, or acetone, whatever you chose. Okay? Some of those will not hydrogen bond, but most of those will dipole-dipole. Okay. All right, so the only ones I want to talk about here is number 3, for now anyway. If the molecule had a very high affinity for the stationary phase, what am I talking about here when I say stationary phase? So but the stationary phase in the procedure is what material? The molecule that I'm talking about, the solute molecule, has a high affinity for the stationary phase. So we have like a little chromatography strip here. This is a beaker, liquid in here. What's traveling up? The liquid solvent, right? So the solvent's traveling up. That's the mobile phase. What's the stationary phase? Huh? No, the stationary phase is the paper. Sorry, the paper is the stationary phase. Okay, the dot that we're talking about is the solute. So what we call the stationary phase, this is the stationary phase. It's the paper. The mobile phase is the solvent. So the thing that we're looking at, the ability to travel, is the solute, which is the dot. So the molecule is a high affinity for the stationary phase. That means that the molecule is staying put where it was placed to begin with. So the molecule is a high affinity for the paper, not the mobile phase, aka the water, solvent, or whatever. Okay, stationary phase is paper, or TLC paper, whatever it is that it's given to you in the lab. So what role does the mobile phase play in the distance the molecule travels in chromatography? What role does the mobile phase play?
Your mind attracted to the solid, you're going to move up with it further.
Right, depends on your. Thank you. So the mobile phase has to have similar IMFs as the solute particles. The more attracted the solute particles are to the mobile phase, they travel more. So the mobile phase is actually serving to physically pull a mixture apart. It's separating it into individual pieces that it's made of based on its IMFs. Okay, last one. If you had combined a polar solvent with a molecule as a carbonyl group, like, C-double-bond carbonyl is the name of that, would it have a high or low RF value? Meaning, first of all, does it travel with the mobile phase, or does it stay more attracted to the stationary phase? Probably with the mobile phase. Like, the carbonyl group is going to be polar, polydipole-dipole interactions. The polar solvent doesn't say it's water, but it's polar, so it can have dipole-dipole. So it's going to travel with the mobile phase more, so the RF value will be high, because RF value is a ratio of distance traveled of solute over distance traveled of solvent. So as it travels more, RF value increases. All right, those are all your dyes. And I'm going to keep this up here for you for later, because I know you guys will need to look at the dyes up close and personal. It's hard to see on your paper, and I like the color-coded nature of this. And if you can't remember what your solvents look like, they look like this. And then I'll work with these questions as you guys go through the lab. But don't forget, you're only getting 20 milliliters of each. But if you need to do more solvent practice to answer any questions, I'm going to give you more. So I'm not going to limit you in solvents. You can do more, but you have to do what I've asked you to begin with, okay? Okay, my groups, I'm missing a couple people. I might reorganize, but I think we're going to be fine. So I think there's at least 2 people per one. I'll show you where everything is in the back. Meet me at the back lab station.